that, now we are going to see how we can find the gas viscosity and the reservoir condition. For that purpose, we are going to use this equation. So this equation says the viscosity of gas is equal to the summation of viscosity of every component of the gas times the mole fraction of that component times the square root of the molecular weight of that component divided by the summation of mole fraction of every component times their square root of molecular weight. Okay, so generally the composition of the gas is given, so we have the mole fraction of every component. We know the gas component, so we know what component we have, so their molecular weights either we know or we can get from the end of the book. So the mole fractions are given, the molecular weight is easy to find, and the only unknown is the gas viscosity. So figure 6.7 gives us the gas viscosity of all the pure components at atmospheric pressure. Okay, so it gives us the gas viscosity at any temperature and atmospheric pressure. Okay, so at any temperature I can find the viscosity, but this is given with the viscosity at atmospheric pressure. So if I read the viscosity from this figure, plug it here, and find the total viscosity, this viscosity will be the viscosity at 1 atmosphere. Then I need to make the correction because I want to find the viscosity at the reservoir pressure. In that case, I do the correction and I find the viscosity at the reservoir condition, which I will show you how to find that correction. Okay, so let's do an example. So calculate the viscosity of gas mixture given below at 200 degree Fahrenheit and a pressure of 1 atmosphere. So here the question asks you to find the viscosity at 1 atmosphere. So we don't need to do any correction for pressure. Okay. So as I said, the components and their mole fractions are given. Okay. So what I can do, I write the equation for the gas viscosity. So I have the equation for the gas viscosity. And this equation, I need the mole fractions, which are given. I need the square root of molecular weights, and I need the gas viscosity. So to find the gas viscosity, the temperature was 200, given 200. So I can use figure 6, 7. At 200 degree Fahrenheit, I draw a line, and I read the viscosity of every single component for methane, for ethane, propane, and N-butane. So I read all these viscosities from figure 6, 7. So I have the viscosities. So the mole fractions was given. The molecular weights, I can find it from end of the book, or I can memorize that. Methane is CH4, carbon 12, hydrogen 1, so it becomes 16. So I can find the molecular weights from end of the book. These are constant values. Then square root of molecular weight, I take the square root. I multiply the mole fraction by square root. The viscosities, these are the values that I just read from figure 6, 7. And I calculate the denominator. So viscosity times the mole fractions times the square root of molecular weight. And then the denominator, which was simply the mole fractions times the square root of molecular weight. So I sum them up. This is my nominator, and I sum this up. This is my denominator. So this is my nominator and denominator. So the denominator calculated here, 0.0538. Denominator calculated here, 4.316. So the viscosity becomes 0.0125 centipoise. Okay. So I can find this viscosity, and this is the viscosity of the gas given at 200 degree Fahrenheit and atmospheric pressure. Okay. So this is the first step. But what if the pressure is not atmospheric? But before that, if the gas mixture is not given and you only have the specific gravity, there is a figure 6.8 that we can find the viscosity at 1 atmosphere by simply knowing the gas specific gravity and the temperature. But we are not going to use this because most of the time we do have the mole fractions, and if you do have the mole fractions, you must use them. So this graph brings more inaccuracy and more approximation in our calculation. So we are not going to use this for the case of finding the gas viscosity if the if we know the components. Okay. uh, but what we can do, we can use this to find the viscosity of heptane plus, because we know the heptane plus are not a pure component, so I cannot find their viscosity as figure 6-7. Okay, because heptane plus is not a pure component, I cannot get that from here. But generally, I do have the specific gravity of the heptane plus, so I can use figure 6-8, knowing the specific gravity of heptane plus and the temperature, finding the viscosity of heptane plus at 1 atmosphere. Okay, so this graph can be used to find the viscosity of heptane plus. So if you have the heptane plus in your components. But to find the gas viscosity at higher pressure, as I said, we need to convert that viscosity that we just obtained at 1 psi at 1 atmosphere, 14.7 psi, to the reservoir pressure. And for that, there are a series of figures or corrections given. And these figures, starting from figure 6-9 to 6-10, 11, 12, these are based on different gas specific gravity. So what we need to do is to first find the gas specific gravity. And we know the specific gravity of the gas was defined as the apparent molecular weight of gas divided by 29, which was the apparent molecular weight of air. So apparent molecular weight of gas was the mole fractions times the molecular weights, and you sum them up. So you find the specific gravity. If the specific gravity falls between 0.65 and 0.9, then we go and we use figure 6-9. Okay. So in figure 6-9, we need to know the TPR, the PPR. Okay. So the TPR and PPR is exactly like the way we found it before. So the TPR is our reservoir temperature divided by pseudo-critical temperature, the corrected pseudo-critical temperature, and PPR is the reservoir pressure divided by pseudo-critical pressure, the corrected one if you have non-hydrocarbon. So the PPR and TPR calculation is exactly the same as what we discussed in chapter 3. So we can find the TPR, PPR depending on the gas specific gravity. We can find the ratio of the gas viscosity over gas viscosity at 1 atmosphere. Again, the gas viscosity at 1 atmosphere we just calculated, so we can find the gas viscosity at reservoir condition. If your gas specific gravity is more than 0.9, so if it's more than 0.9 and less than 1.2, then we use this graph 6-10. If it's more than 1.2 and less than 1.5, we use this graph 6-11. And if it's more than 1.5 to 1.7, we use figure 6-12. So depending on what's the value of the gas specific gravity, we can use either 6-9, 6-10, 6-11, or 6-12 to do the correction for the reservoir pressure and find the viscosity at the reservoir condition. And that requires us to know the TPR and PPR value only. So here's an example to calculate the gas viscosity at the reservoir condition. So as I said, we need to find the specific gravity of the gas. So if you find the specific gravity, the gas viscosity at 1 atmosphere can be obtained from figure 6-8. Remember, in this equation, the mixture is not given. Okay, so only the gas specific gravity is given. So it's okay to use this. But if the mole fractions are given, we have to just go with the previous discussion where you had to find the viscosity of the pure components, and then use that equation to find the viscosity at 1 atmosphere. But here, since the gas specific gravity is only given, we are using figure 6-8. So now I have the viscosity at 1 atmosphere from figure 6-8, and I have the apparent molecular weight of gas, which is basically 29 times specific gravity. I'll go and find the TPR and PPR values. For that, since the gas specific gravity is given, I can find the pseudo-critical temperature and pseudo-critical pressure from figure 6-10. Okay. And then I can find the TPR and PPR. That's the reservoir temperature divided by pseudo-critical temperature, reservoir pressure divided by pseudo-critical pressure. And then, since the specific gravity was 0.8, then I can use figure 6-9, which is for the specific gravity between 0.65 to 0.9. Now, knowing the TPR and the PPR, I can read the ratio. So the TPR we found it, the PPR we found it, we find the ratio, which is 1.5. Now the viscosity at the reservoir is 1.5 times the viscosity at 1 atmosphere, which we had previously. Okay, so this is another example of finding the gas viscosity. But again, as I said, for your exam, most probably what you will have is the mixture given. So what we will have for your midterm exam is to find the gas viscosity at the reservoir condition when the mixture is given. And when the mixture is given, basically what you are going to do is, like here, when the mixture, like this example, like when the mixture is given, okay, so you have the mole fractions, you read the molecular weights, you calculate this denominator. For the denominator, you need to have the viscosity of pure components. You find that from figure 6-7, and then you can find the viscosity at 1 atmosphere. So now that you have the mole fractions and molecular weights, you can find the apparent molecular weight divided by 29 and find the specific gravity. And depending on what the specific gravity you got, then you can use figure 6, 9, 10, 11, or 12 along with TPR and PPR values to find the viscosity at the reservoir condition. So your exam question could be something very similar to this. The only difference would be, instead of finding the viscosity at 1 atmosphere, I will ask you to find the viscosity at the reservoir condition. Okay, and you will have homework assignments to work on this type of examples. And the homework assignment that I'm going to submit today is basically contains both of open book questions for your midterm exam. So please go over that carefully, and if you have any question, let me know, and we'll go over that. Okay, so this is the end of our chapter number 6, and then in the next video we'll start the properties of the black oil reservoirs. Okay, and by the way, this is the end of the part for our midterm exam. So the midterm exam would be from the beginning of the class all the way to end of this discussion. Okay, and after that is basically will be covered in our final exam.